So this question is related to the gravitational field and Newton's law of gravitation. First question 3. The International Space Station is an artificial satellite in a low Earth orbit. The International Space Station has a mass of 4.19 into 10 to the power 5 kilogram and it orbits at a height of 4.1 exponent 5 meter above the Earth's surface. The radius of the Earth's surface is 6.3 exponent 6 and the mass of the Earth. Calculate the time taken for this International Space Station to complete one orbit of the Earth. So this is our Earth and this is representing an International Space Station. So this distance is 4.1 exponent 5, this distance. And the radius of the Earth, that is 6.37 into 10 to the power 6 meter. So what is the total distance between the center to this International Space Station? That will be the sum of these two. So first we'll use a Newton law of gravitation because when object move in a circular path, like this is moving in a circular path, so here the centripetal force is equals to gravitational force. Gravitational force is given by, like mass of a satellite is small m, mass of the earth is me. So capital G, mass of the earth, mass of a satellite divided by radius square. And centripetal force is given by mass of an object which is moving in a circular path multiplied by speed divided by radius. So this R will cancel out with R. The mass of a satellite will cancel out each other. So what we are left with? We are left with that G is equals G into mass of Earth divided by this is not the radius of Earth, it's a distance between the center of the Earth to a center of mass of a satellite, which is R, into V square. So first what we do, we'll work out at what speed it is moving. And then we can also use like speed, like speed is distance divided by time. When object move in a circular path, speed is distance divided by time. So after working out the speed, the distance that is equals to circumference. So it will be 2 pi r and divided by t. If we need the time period, so time period will be equal to 2 pi r divided by v. V we will have from this formula and r already we have. So we can work out the time period of this artificial satellite or International Space Station. That is about 5,500 seconds. So just substitution is there. I'm not substituting the value. The gravitational constant is there. Mass of Earth is there, but R is the distance. This is R actually. So R is there. You and take a root, under root, you will get value for V. After getting a value for V, you already have R. So 2 pi multiplied by R divided by V, you will get the time period. The next one, calculate the gravitational field strength by the Earth at the height of International Space Station. So how we can work out? We have the formula that basically if we say that the Earth is pulling the object is also pulling the Earth, so that is equals to its weight. So we can say weight is equals to gravitational force here. So W is equals to gravitational force. Weight is mg, so mass of a satellite, the International Space Station, and the gravitational force is g, the mass of the Earth, the mass of the satellite divided by r square, where r is, again I repeat, it's not the radius of the Earth, it's a total distance between the center of the Earth to the center of this International Space Station. M will cancel with M, so we can say the value of the G is equals to capital G, which is a gravitational constant, mass of Earth divided by distance between them square. So we have the G, we have mass of Earth, we have R, so we can work out the value of the G is constant. That will be there at the end of the exam. You will find the value for the constant. 6.67 into 10 to the power minus 11. The mass of the Earth is 5.98 into 10 to the power 24. divided by the distance, which will be 6.37 into 10 to the power 6 plus 4.10 into 10 to the power 5 and then square. So this will be about 8.68 Newton per kilogram. That's the value for the gravity. Astronauts on board the ISS, the International Space Station, experience apparent weightless conditions. Why the gravitational force exerted on the astronaut by the Earth appear to be absent? Like why they experience that a weightlessness condition? Because what happened, the gravitational force is actually providing a centripetal force. So they don't experience, like the force which they experience is causing the circular motion. That's why they don't feel the gravity. And so there will be no reaction force on the astronaut. So if astronauts on the space station, and this is the Earth, the Earth gravity is pulling, but that gravity is actually because the space station, the International Space Station, is moving in a circular path. So what happened? This causes circular motion. So this force is responsible for centripetal motion, the gravitational force. That's why inside they don't, because the force is used to move them in a circular path rather than attract toward the center. As a result, what will happen? They experience apparent weightlessness condition. If they were stationary, like example, if this is International Space Station was stationary, not orbiting, in that case, it will be attracted towards the Earth, and that time they will experience the force. But if they fall with the acceleration due to gravity, again that will be weightlessness condition. Like if their acceleration is same as due to gravity. So main idea is that why the astronauts does not experience any weight, or the orbiting astronaut is effectively in a free fall towards the Earth, and the gravitational force provides the force which is required to produce a centripetal force. So we can say the gravitational force the gravitational force is providing a centripetal force as a or move the astronaut in a circular path, the International Space Station in a circular path. As a result, what will happen? So they don't. So there will be no reaction force in the astronaut, and they will appear as, so no reaction force on them. As a result, they will not experience any effective gravity to experience that a weightless condition.